So hello everyone. Okay. Hello everyone. My name is Shagwal and I will be the host for this event for the first part. And a very warm welcome to all of you. It is our 28th event, spring event, and the weather is so perfect. I mean, the weather in Berlin just could not be better. And it's a shame that we have to meet online for this event. I wish we could do this in person, and hopefully in the next couple of months we can have an event in person and see you all and have those pizzas that we all miss. Nevertheless, for this time we have online and we have 3 excellent speakers planned for you. But before that, a short introduction about who we are, what we do, and why you should attend more and more PyBerlin events. So why PyBerlin? Well, Python, the snake and the code, arrived in Berlin and it saw the TV tower and it climbed the TV tower and started exploring Berlin. And that's how it fell in love with Python and Berlin. And through this platform, we want to share ideas. We all love Python. We're all based in Berlin or somewhere around Berlin, or have been at some point connected to Berlin through work or through travel or any other creative idea. And we welcome everyone who is interested. Our organizers are Anesthesia, who is handling the streaming platforms and is one of the most active members among all of the organizers we've had on this platform. Then there's me, Theo, and Lubin, whom you would be interacting with in the later part of the event. Thank you everyone for joining. This is our 14th online event. I think we started last year around March or April when lockdown happened, and we're so proud that we could organize one event per month since then. And that's why it's our 14th event, and hopefully the next 15th or 16th event would be in person, and this online would be scrapped from here. We don't have many rules and regulations, but one thing that is very important for us is that we be nice to one another, be the organizers, the speakers, or the attendees. We request all of you to be patient, to be kind, and respect each other. If you're interested in our code of conduct, then the link is visible on the screen. Please check it out. It is a very safe place to ask questions, and there is no need to feign surprises or well actuallys or subtle isms. By isms, we mean racism, sexism, or any form of discrimination. We want this platform to be very inclusive, and we hope that you all respect one another and enjoy this platform as much as we do. Today's event is sponsored by ScoutB, and Anesthesia works for ScoutB and made this possible. The Zoom link has been provided by this company ScoutB, and we are very thankful to you. So thank you so much for helping us in the logistics and making this possible on Zoom as well, along with Twitch. Today's agenda, we have 3 interesting speakers. First one is Ivan, and he will be talking about retro game dev, making your own compiled language for NES in Python. Our second speaker is John, and he will be talking about agile knowledge graphs. And then we have Naomi, who will be talking about a slice of Python. All 3 talks look very interesting, and we look forward to that. Along with that, we have collaborated with Manning Publications, and we are providing, along with them, we are providing discount codes for books that you would like to purchase by Manning Publications. You can use the discount code as mentioned on the screen to get 35% off a book of your choice. And you can also scan the QR code mentioned on the right. These links and QR code is also visible on our Twitter platform or on our Meetup platform. So if you're interested, or just reach out to us and we will be very happy to share with you. We also have a raffle for today's evening, and the winner of this raffle will get a book titled The Quick Python Book by Naomi. And to enter the raffle, please fill the form mentioned on the screen or scan the QR code visible on the screen. These links will also be made available in the chat section or on our Twitter page. So please feel free to join and in fact, share it with your friends and family as well if they would like to join, and let's see who wins this raffle. Along with that, a little more on the logistics side, we are looking for organizers. Specifically, we're looking for people who would be interested in handling our social media pages, such as Twitter, LinkedIn, and helping us grow and helping us increase our visibility on such platforms. So if you're interested in doing this, then please reach out to us. Even if you are willing to help us in organizing these events, such as organizing the speakers or coordinating with them, please reach out to us and we will make it possible. We're also looking for speakers, people who would want to share their projects, ideas with us. And when I say speakers, do I mean just professional speakers? Well, not really. I mean, along with professional speakers, we're also looking for people who have something to share, be it a project, be it an idea, or whatever you would like to share with our audience. Or if you would like to practice for one of your bigger conferences and would like some feedback from the people or have some interactive Q&A before your big event, then please let us know and we will schedule something on mutual convenience. We have two formats for the talk. One is a 30-minute talk with Q&A, and then we have short 5 to 10-minute lightning talks, depending on your requirement. You can choose either of them. And also, if you are starting or if you don't want to have a Q&A, that is also possible. If you're interested, then please submit your proposal here. You can see the QR code and the link, or you can just reach out to us via Twitter or Meetup, or reach out to one of the organizers personally, and we will make sure to find you a spot in the coming months. Our next meetup is planned for June 21st, 2021, and it's a Monday. And in fact, we're also looking for speakers for the June event. So if you're interested, please let us know. And also our audience, please mark your calendars, and we will be back with an online meetup for this time, but we are looking into organizing something in person as well. We would love to hear what you think about our platform, good or bad. If you have any feedback for us, then please let us know. Also, let us know how you find this event by tweeting about us on Twitter. And if you would like to tag us, then our handle is PyBerlin Python. Also, don't forget to follow us there. We post about our events, our raffles, or collaborations on Twitter quite frequently. And also some credits. The free assets and resources, the presentation template was created by Slides Carnival, and the photographs were by Unsplash. And people who helped with this logo and story and these presentations together were Elena, Konstantin, and Christian Barra. So thank you, all of you, for making this possible. We have been using these logos and story all through the last couple of years, and we find it very, very interesting, and we're very grateful for you for putting your time and energy in creating this. So thank you so much. And with that, let us welcome our first speaker, Ivan, who would be talking about retro game dev, making your own compiled language for NES in Python.
Hi, everyone. How do you hear me?
Yes, we can hear you.
All right, super cool. Thank you for having me in your super warm event. We're really glad to be here. I will share my screen right now. And here it is. So, a few words about me. My name is Ivan Nikolaev. I work as a tech lead at Wargaming, where with my team, we are making the gameplay logic for our flagman game, World of Tanks. But in this talk, we will be back in time for something like 35 years ago when the NES was released. And we will see how the elders made the games back in time, and how you can improve a bit on that. Instead of writing raw assembly, how can you make your own compiled language for this platform. So you will ask, like, why I ever need this, like in 2021? I mean, writing a language for a system which is dead, and what are the profits of this? Actually, writing a compiler and a language is a very enlightening experience, because you will have the possibility to understand how the actual hardware works, and that will definitely improve all your skill set for day-to-day programming. And a part of that, the NES platform, for example, its architecture is much easier than anything we work nowadays, like the x86 platform or ARM or whatever else. It's much simpler back in times was, and you can study it without this super steep learning curve. So let's jump in. What's a Nintendo Entertainment System? Well, basically it's an 8-bit console. It was released back in the 80s and actually changed the market. It relaunched the whole game industry. It is still sold in a few countries, probably. Not sure, but nonetheless, it's still kicking and running. You can buy it in the stores or one of its copies. A lot of games were made for it, so finding something to play is definitely, I think, not so hard to do. And most of the games, you have seen them, they become like memes. So they are still around today, and most of the franchises, the popular ones that we have on our super modern, like 12-core CPUs and so on, started with their roots back in time. Let's take a look at a few of the games. For example, Mario, I think like everybody knows about it. The little plumber who fights for his princess by defeating like turtles and mushrooms. Well, that at the time was a game design which revolutionized the whole genre, and in all its reincarnations, it's still present even today. The Legend of Zelda, basically one of the first role-playing games that started like in digital form. So back in time, you could only play with your friends on tabletop by rolling dice, and with Zelda and similar, it started like to be digital, to be interactive. So you had like your Link character roaming around with his sword, defeating enemies, exploring the neighborhoods, and so on. One of my favorites, like the Teenage Mutant Ninja Turtles. I mean, it was a very hard game to finish actually, because there were a lot of enemies, moves, dangers, and complex levels. It squeezed out every bit of the platform, and definitely was a piece to try back in time. And I mean, yeah, like infinite hours spent here on the tanks, the Battle City actually, back in time with my friends on the TV set, trying to play together. It was a party game to play together against the bots controlled by AI, the primitive AI of the Nintendo console. For this game, even like World of Tanks has its own, as to say, like Easter egg or tribute. If you zoom out like this big battle map, you can see that it resembles exactly the Battle City game, which was back in time, from which probably took inspiration. Even like the score, it was rearranged from what, like that 8-bit sounding pattern. But yeah, let's move back into the past. So not enough modern graphics. Let's see what hardware it was running on. I mean, the hardware specs probably won't make anyone say like, wow, so power. But yeah, it was something like this. It was a variation of the MOS Technology 6502 CPU, which had just the clock frequency of 1 megahertz and 8-bit of data bus. So you could work like these tiny instructions running on this CPU, crunched 1 byte at a time. So you make your game basically one byte at a time. So you make all the arithmetics. You have no floating point numbers. You have no large integers like 32 bytes or like even 64. Just forget it. You have to code it on your own. And you have like this 16-bit addressing bus. Basically, that means that you can see from this CPU, you can index, write, and read to at most 64K of memory. And to make things harder, only 2 of those kilobytes were actually RAM. So for all your like dynamic data, like the position of the characters, the health points of the enemies, the score points, the money, whatever you could have there, which changes in time, you have 2 kilobytes to fit in there. So you cannot even remotely think to have a Python running there. And the actual graphics was displayed by this PPU, which is the precursor of modern GPUs. It was capable of like 256 by 240 pixels screen resolution of your TV set. You could use at most 64 colors, and you couldn't even like draw by pixels. There was not enough power to process all the pixels by this resolution in one frame. So you could just draw by having these boxes, 8x8 sprites, as they call them. And everything here is basically made of sprites. And you could use at most 4 colors at once. If you look at Mario, it was like yellow, red, whitish. Yeah, 3 colors actually, because the fourth is the transparency. So 3 colors of 64 per sprite. Super cool graphics, very realistic. Actually, the 6502 CPU wasn't famous only for being part of NAS. The whole Apple empire started with this Apple II computer, which also mounted the 6502. And the demonstration that it was like future-proof enough, even like Bender from Futurama had it like piloting his brain. And even more, like the T800 from Terminator, if you stop the frame, the image at the right time, you can see what while he's chasing his victim, the assembly code for the 6502 is scrolling like in his brain somewhere. So let's dive into actual programming of this. How does it work? Basically, you have the CPU as the central part, the central processing unit. And as you saw, it just can read and write to memory. You have these 3 registers that you can program, a few bit more that are handled internally, but that's like too low detail. We don't need that. The only thing that you have to know is that there was an operating system, no SDK, so no DirectX, OpenGL, or whatever, no library. So you cannot just have an instruction that draws something on screen or asks for a button of the controller. So how do you ever make a game with that? Well, basically there's a technique called memory mapping of devices. Of these 64K, only 2 of those are memory that you can actually write and read to. The other regions are mapped to devices. So when the CPU says, all right, let's write at this address here, which is specified in the documentation, a byte, the CPU doesn't know where it goes, but the memory controller knows that that region of memory is mapped to the video chip. So you can instruct the video PPU make something like draw something on the screen, for example. So if you are going to make the Mario jump, you press a button on the controller, and that press triggers a bit high at some known location of memory. And at that point, in your main loop, you can write the instructions that read that memory and perform some logic based on that. And for example, if the logic is to make the Mario jump, all you need to do is write to the video memory location the coordinates of the sprite a bit higher by the Y coordinate, and having like the right sprite with right colors and so on. So that's it. You make games just by manipulating memory. So how do you do that? I mean, you are using like the assembly language. And to see an example, let's compare like Python. Suppose a super dumb code here. We have a byte array. It's written like this for purpose. I mean, it could be one-liner, but anyway. So filling up it with 7s, for example. The counterpart in assembly would be something like this. So initializing registers, doing some comparisons, transferring data, decrementing, incrementing, and jumping back. So looping for a bit and then ending here. You don't have to understand much of this until the moment you start like to write the actual compiler. But yeah, that's just an example. So looping enough, but how a real game looks like. Here is the project. It's a real world example. It's a game I'm making with a friend. And so, it's the pinnacle of the game design. Basically, you have a spaceship, you have a scrolling stars background, you fight these strange dudes like UFOs, space octopuses, and so on. You have collision detection, projectile firing. Once the enemy is hit, you have like your scoring. Well, super simple. I mean, this probably could be done in something like 100 lines of Python code, maybe. Well, I suppose like 70 are enough. Well, it's 2,500 lines of assembly code, most of which I probably is like comments, because it's too low level to understand the actual game logic which is behind it, because those are instructions to the CPU. It's something that you cannot just look at it and see, oh, right, so this is my draw function. No, okay, so these fragments of code actually tell the PPU to write the pixels a bit scrolled down, to like query the memory where the controls, like as seen here in the animation, are pressed. So you perform some logic based on that. And so obviously it started to, I mean, to be a pain. Maintaining this code, even like dividing and commenting it, it's very easy to do errors and so on. So nothing better to do than writing a custom programming language. Why not? Actually, because you cannot have like even C compiled for that platform. It's too complex. Its data types are too complex. Not talking even about Python, because the runtime would never fit that and the CPU would never be able to run it. So you need like something on your own. Well, feels super cool, right? But yeah, writing a programming language and the compiler could be pretty tedious. So you need a good language to write that for. So that's why it's Python. Obviously, I won't be in this like meetup if it was a C++ one. But anyway, yeah, we use Python. So the requirements for this language, what they were. Actually, it has to be obviously compiled for the 6502. It has to have like this Python-like syntax. So very Python-ish style of coding. So indentations as block dividers. Well, func and var are just our inventions because we like them more than def. But anyway, it should fit like Python, be super easy to read, to write, pretty simple. Should support a bit, obviously, like 8-bit variables and 16-bit pointers, because we need a way to write at some custom arbitrary locations of memory to be able to communicate with the devices. And arrays, obviously, something like we have to be able to iterate over something to do bunch operations. And if you're going to make logic, you need conditionals, you need loops to loop other things, and to not get mad and copy paste stuff around, you need functions. So here it is, like super minimal example of a function setting up some array of known size into known value. So here it is. Obviously, it's your own language. The most important thing is the name. So what I was thinking about, like it is targeting NAS. It should be like made for quickening up the development. Yeah, sorry, I didn't came with something better. But yeah, that's it. So Nesquick, 2 minutes like compiler theory. What you write in your Visual Studio Code editor is here on the left, and what you have to feed in your processor is here on the right, machine code. It has to undergo a few transformation stages in order to get like in some sort of form which is understandable by the CPU. The first thing like the compiler does after it has read the file from disk is the lexical analysis. It just divides the incoming characters into sequence of tokens, and those tokens are something that you can work on. For example, the for, while, I don't know, true, false, the colon, all these are keywords and special, which have special meaning for the language. So you have to divide the pretty raw string that is coming from the file to this sequence of tokens. Then you take them into the parser. This is where the place actually that validation of the rules, the grammar. So for example, like in Python, defining the function like the df, func name, parentheses, arguments, colon, space, and so on. So this is validated at this stage. And after the parser has validated your code, it creates the AST. So the abstract syntax tree, which is the data structure, which is suitable for performing the actual code generation or intermediate representation generation. This is done in advanced compilers like real world compilers like the Silang or GCC, but we are not doing this. We are just transforming AST into machine code. I'll show right now how. The Lexer actually is a very simple thing. If you think about it like a state machine, it yields like tokens based on some rules, and usually these rules are pattern matching. So imagine this very simple arithmetic expression, well, like everybody knows, not only from programming, but like from basic school. So we want to tokenize this. We start by expecting a number, and then we expect either other numbers like coming back into this state, or like operators, like symbols which are plus, multiplication, and so on. So we start to iterate over it and just yield states. If you find something that is not recognized, we throw an error. So the famous, unexpected token error comes from here. So going over it, we create like the tokens for this. We finish the stream and we go to the end. So we have our token list, the num2 operator plus num4 operator times, and so on and so forth. So we have like to create the tree for this, the abstract syntax tree. Here comes the parser. So the parser for this sequence of tokens, for this expression, should yield something like this, because also the rule of associativity and precedence apply. We have to create a tree where the multiplication, being the topmost priority thing to do first, has to be like a branch. So branch is here and isn't the operator, and the leaves are the operands. So afterwards, 4 times 3 should be divided by 2. So here it is, and we go up the tree. So the result of this should be added to 2. And that's how our parser works. So branches, operators, leaves, operands. Fortunately, we don't need to write anything on this, because there is this fantastic library, which is Lark. It allows you to auto-generate the scanner, like the lexer, and the parser, by feeding it the formal description of your language. So the only thing you have to worry about is define the grammar, the rules of the language. It's actually a super funny thing to do. And BNF is pretty simple. BNF is the de facto grammar description notation, and it is extended form like EBNF. You can Google it on Wikipedia, and it's explained pretty well. But to be short, like on the left, you have the rule, the name of the rule. On the right, you have like the patterns which should match or other subrules. It can be like arbitrarily recursive. For example, for our like super simple math language, the factor, which is the number, is any digit from having 1 digit at least and infinite more, or an expression like here's the literal for the parentheses, and an expression. Expression in its term is like either a term or a binary operation. Binary operation is a recursive rule, and so on and so forth. So by this, you define 2 things. The patterns that have to match their order, so like where you place the tokens and so on. So this is actual syntax, and also the precedence of the operators. So coming from bottom up, the most important thing is the number. Then comes the operator, division and multiplication coming first, addition and subtraction coming second, and the lowest priority of the whole thing here is the expression. BNF allows you to define arbitrarily context-free grammar. So you have to consider that computers are deterministic machines. And for example, if I say like Python is cool, that could mean like 2 things: that I found a dead snake, which is just cold, or that Python is a super awesome programming language. And you cannot allow that ambiguity to the computer. You have like to tune up your grammar to be always yielding one thing. And it's fully supported by Lark. Let's see how it is used. You just copy the previous example, add a few annotations, like something which Lark can ease. He's working on this. Basically, the annotations are just to saying that I want to have a separate meaning for the plus, like let's call it an add rule. And for the subtraction, like the sub rule, we will need this later. We just give mnemonic names to the actual thingies. And we use it like this. We just import the Lark, feed it the grammar, and we have our parser. Super easy. This parse function just, whatever is the source code, feeds it into the parser and prints like the pretty form. So for our expression from before, for this string here, it actually creates the abstract syntax tree. So starting from the start rule, which is this one, the whole expression, we have then the leaves, the branches and the leaves. So the second lowest priority that comes is the addition. So of 2, like the leaves are 2 and another operation, like the division and multiplication. So in this case, we will create another tree, subtree, the division of multiplication and 2. So here it is, the representation of it. With this tree in mind, how would you then transform it into something like code? I mean, something compilable and understandable by the CPU. So let's take a look at the actual what the tree is. I mean, what each of this node is. Super simple. I mean, the lark tree object has like 2 properties of interest. One is the children and another one is the data. So either like the name of the rule or the actual content. So yeah, for this super simple tree, like this arithmetic expression, you will have like start, which is a node, and it will be named start. It has like children, in this case just one, the sub. Then and in its turn, it will have like 2 children, the add 3 and 2, like the token 2. Traversing this is super easy using like the visitor pattern. Because Lark provides you an additional class like called interpreter, and it works super simple. You have to define methods which are named the same way as you named your rules in the BNF notation. So it will descend the tree, and for each of the node it finds, it will call the name of the method with the same name. So for example, starting from top down, we reverse this behavior from bottom up, because in the start node, we say like visit children, and it in turn will call the first children will be like sub and add and so on and so forth. So infinite like tree, whatever complexity, it will just call the methods one at a time. So let's see how the sub operator yields some actual assembly code based on this approach. Suppose we are here, like we have our previous expression, we descended the start node, we are now at the sub node. So we receive like the tree as an argument, the method is called. We have first obviously to evaluate the children, because we have to know like to subtract what from what. So first the children code is generated, then whatever is left there on the stack, if you wish, we insert the actual instructions. These are just a super simple function, we'll show it later, but it just prints out, you know, the actual opcode for the processor. This one is just an enum, so I could just use the quotes for ease, but it's not the default. So visiting children first means that we started when we have to interpret like here the add tree. So let's go for it. Add function, super simple. I mean, we unpack the children, we visit each one, and in this case, these instructions, I mean, without going into much detail, are just related to loading whatever is here into register A of the processor, visiting then the red expression, and adding to that register whatever was in the red expression. So the actual instruction method is just a print, as I said. I mean, it's just a pretty printing, so I can debug this, take this code and show it into a working compiler just for check. But yeah, I mean, just to not complicate everything there. So after executing that on the tree, the first operation to be produced will be LDA4. So load into register A number 4, clear carry flag, add to whatever is in A, add to it 3. Then we go up, and after having visited this, we create the other instructions, the subtraction ones. So like clear the carry flag and subtract with carry 2. Here it is. I mean, this is a working assembly code that you can like compile and put into the processor. Suppose we want to do something nonlinear. I mean, expressions are fine, but we can do that in a calculator. We want to add some logic. In this case, we have to augment our grammar. So we are introducing Python-like if else statements, and we just extend the grammar. In this case, start is not anymore an expression, is a statement list. And the statement list is a statement or a new line in any number, like the start here, regular expressions, you know. The statement here could be an if block. So if stment is the if block, or a return. So this way we can have like nesting ifs and returns. So super simple. Let's go and see what is an if block. It's an if branch, elif branch in any quantity, and else branch. Could be just one. The if branch looks like this. I mean, this part of code is, the rule for it is like if keyword, like quotes, so literal if, expression, whatever is, we already saw it, and defining the body. So a colon in the body. Elif is the same, just changing the keyword. Else is the same thing without an expression. So the body is just a statement list, but wrapped with an indentation. So like here, return is just literal return and expression. We have to augment a bit the expression, and having also all like old term been up, we had also the comparison expressions, and everybody who programs Python knows what they are. It's just expression, special symbols like for Boolean comparisons, sorry, for arithmetical comparisons, and we define aliases for them, as we did for the addition, subtraction, and so on. So nothing changed here except for the factor, because we want to use also variables like letters here. So factor is either a number, expression in parentheses, or a name of a variable. This is just a placeholder for, identifier. And here it is. I mean, parsing this using our lark parser will yield something like this: a start node, and then the if statement, which is the whole thing, and the if branch. The if branch, the first one, is just a node, a branch with two children, right? The leaves. So the first one is the equality condition, like equality check, where it's like a reference to A and 3. So equality check. The body is return 3. Elif branch in here is like the lesser than ref A to 3. And the else branch doesn't have the comparison expression. It has just the body. So the code generator for this will be structured like this class here. You define just the methods. I won't go much deeper because actually time is running. But yeah, actually, the example is pretty similar to what we did for arithmetics. And for this code in Nesquik, the compiler will produce something like this code in assembly. So it will define the labels. It will like load the register, do all sorts of computation like comparisons. It will jump to other branches if, for example, that condition wasn't true, and we have like 3 different branches, but a bit more of labels. That's like internal stuff, how it works. But yeah, the labels define the entry points for where you go. So a super quick example I have specified previously, like for what was our requirement for Nesquik, was like this memory setting function, and it will compile into this assembly block. So we have the functions, you have the registers manipulation, you have the stack handling, you have the conditionals, looping, everything is in here. So how you feed it actually into the processor? Well, the process of transforming assembly into bytecode is super simple, because one instruction of assembly corresponds to exactly one instruction in the processor. So LDA will be something like A9 mnemonic, so byte A9, and its argument immediately coming after. In this case, like A9, 00, this thing for the processor means load 0 into register A, and that's pretty it. So one thing I learned from this experience, more than even like from production code, is that anything for which you don't have tests just doesn't work, because you cannot try it until you have your program run and you want to be sure that your compiler is generating like working code. So I use like PyTest as everyone, and Py64 is just an emulator for the CPU like 6502, and it allows you to execute bytecode on that and expect like the memory and the registers. So you like create a little wrap-up class around it, which just compiles your code using the compiler and loops over it until an interrupt is found. And that way you can like test things like this. For example, you write your test expressions unit test, which is, I'm here just testing expressions. So this is code in Nesquik, and here stay the values I want to do test against, so I know that are valid. This previous fixture I wrote just compiles the code, executes them, and the only assertion I make is that CPU should be in a known state and its register Y should have the same value of the expected result. For the functions, it's very similar. Suppose I have two global variables, super dump functions. So the foo one adds 5 to A, the B1 bar 1 returns B. So it should be 20 plus 5 plus 5, 10 plus 20, 30. So after executing this function, this code, this program, I should find 30 in the Y register. And you can have generated tests with templates, whatever. I mean, this code is executed 4 times, replacing stuff here. Each time it expects a different value based on the branch I'm entering in. And it's the way you test your compiler. So with actual code that will be executed by the actual game console. So for those who survived, just few takeaway points. Well, writing a compiler is not that difficult. I mean, you have to learn the architecture which stands underneath, but it's a pretty interesting and nice project with some exceptions. As soon as you start to deal with stack frames, local variables, temporaries and functions and so on, you will start to learn a lot. And you also will understand quickly how your day-to-day programming in high-level languages like Python and so on, what the actual thing that you write, like the for loops, the generators, whatever you like in Python, like the decorators with passing a lot of arguments, the stack handling using, defined local functions and closures and so whatever. You will look at this at a very different perspective, because you will understand that actually some constructs will cost you a lot of CPU, a lot of memory, or could be inefficient, even in interpreted languages, because what the interpreted language does, I mean, in runtime, like in Python, basically is pretty much the same. It's just adding a few more levels, but anyway, it's a lot of, for some constructs, it's a lot of tasks. And 6502 is really simple, actually. If you want to learn computing, to learn not only game consoles, but the basics of the fundamentals of computing, it's much easier to start with than the x86 that we use every day. And because it has very simple CPU, very limited resources, and very few instructions, the x86 is just, I mean, it's a lot of stuff. This whole project, until this completion, was 2,000 lines of Python code. So the compiler itself took less code than this super simple game we made previously. And it was Python coded on assembly. And yeah, tests are not an option. They are a must. I mean, for this task, take it for granted. So thank you, everyone. I run a bit out of time, but hopefully you found this interesting. If you want to know more, there are some links to the socials. You can find the actual code for the compiler on GitHub, the game itself. You can subscribe to my page on Facebook or Twitter and follow up the development of this stuff. Yeah, the glitches are left on purpose because, it's assembly. So that's pretty it, and thank you.
Thank you, Ivan, for the insightful talk. Now maybe we can take some questions. If you have a question for Ivan, you can write it in the chat or in the Twitch stream, and I will relay it.
No questions, apparently. That was either super fast or super clear.
I have a question, actually. You mentioned about the Lexer, you need to create state machines. How many state machines do you need to create? Was this a complex task? You mentioned you use some sort of a library that does this for you, but
yeah, initially I started to write that on my own because I wanted, to learn the whole process on my bones. But it soon turned out that writing a Lexer and a parser for a complex language could be a Python-like language is really a lot of effort. And I was interested in having something working as soon as possible. And searching around, I found like this excellent Python library, Lark, that does exactly that job. So it creates the state machine for you, because it can interpret the rules of BNF, and it can, in a deterministic way, compute all sorts of states that this machine will possibly be, and do it also in a very efficient way. So nowadays there is like almost no reason for writing your own parser. Like you have Bison, for example, and Flex for C world, and you have Lark for the Python world, and it works just like a charm.
Thanks. All right, so if there are no more questions, maybe we can go to the break. Organizers, are we?
Yep.
Yeah, all right.
Well,
5 minutes break.
So
Thank
yeah,
you.
thanks a lot for the great job, Ivan. We have a short break, and we'll continue with the next talks. All right, welcome back. We are going forward with our second talk, Agile Knowledge Graphs from John Volhan. So John, when you're ready, you can share your slides and have a great talk.
Awesome. Let's see. Is that showing up?
Yes.
Great. Awesome. Well, we're gonna jump way up. So we're going from assembly code all the way up to kind of like systems architecture, high level talk about one way we can use Python to manage data, especially large companies, but increasingly smaller organizations are using knowledge graphs as well. And so, you know, sorry for the rapid switch here in scope and attention, but hopefully you guys enjoy this talk. Let's see. So what are we going to talk about today? Go over the agenda here first, right? And then I'll give a little introduction about who I am. We'll talk about knowledge graphs and what they are. We'll talk about things you can do with knowledge graphs. We'll address a question that people have about knowledge graphs, which is, you know, so what? I've heard a lot about graph databases and what does Python have to do with that? And then, you know, we'll talk at the end and throughout about the specific roles that Python plays in the knowledge graph ecosystem and how as Python developers we can contribute to knowledge graphs. And we'll have some time for Q&A at the end. So with that, I'm JT Wolhan. I am a senior AI engineer and architect for a consulting company here in the United States. One of the things I oversee is the development of knowledge graphs and a lot of the analytics to support that and the big data systems that underlie those knowledge graphs. I'm also the author of Mastering Large Datasets with Python by Manning, which is my first book. And then I'm working on a book right now, Knowledge Graphs and Deep Learning, which will be my third book. That's going to come out. Well, I think it'll be released for MEEP late June, early July. So that's the Manning Early Access Program where you can get access to the book as it's being developed, and learn all about knowledge graphs on the way. So that should come out, I believe, February of next year if I hit the times right. So you know, if you are interested in knowledge graphs after this talk, hopefully you don't have to wait too long. So what are knowledge graphs? Knowledge graphs are, were originally kind of brought into the public attention by Google as a lot of big data things have, right? They have quite a bit of data over there. You know, an internet's worth maybe. And they had this idea of things, not strings. And so they wanted to go out to the web and retrieve information for you for your searches, you in kind of thing groups instead of just text strings about an object, right? And so over on the right of this slide here, you can see two examples of the types of products that we can produce with a knowledge graph. These are search cards. These are super popular now, and with all the major search engines, a lot of businesses and enterprises are starting to use search cards for their internal databases and internal search needs as well. And the idea here is, we know with common sense the right things to show someone when they search for a person or a place, right? If you're searching for a person, you want to know, what's this person famous for? What are the top things we need to know about them? Who are related people, right? If you search for a place, you're looking for, well, look, Microsoft at the bottom here thinks you're looking for the weather. They think you're looking for tourism information. You might be looking for resources where you can go to find more information about these places, especially from sources you trust, like Wikipedia, or with respect to a place, right? Maybe like a government website, such, right? So knowledge graphs are a way of connecting of all this information together, and we do this by identifying real world phenomena typically from big data sources, and then we're representing real world relationships between those elements. And so you can have your kind of open knowledge graph context where you've got a search engine that's crawling the web and trying to document facts about everything. But more frequently, we have kind of closed universe knowledge graphs where I'm an organization and I'm bringing in some information about the outside world and coupling it with data that's generated by my business, so by my customers or what transactions, et cetera, and trying to merge those together to try to come up with a better picture of what my business is. And one of my personal favorites things about knowledge graphs is that we get to use a lot of the theory of knowledge ideas, but we don't get bogged down in the strictness. So a lot of the knowledge graph advances come out of academia and information science, and there are people who do things like ontology management is what they call it. And ontology design and taxonomy design, and it's all very theoretical about this is how you should store information to do this, and information has hierarchies, and that's important, but a lot of the times as engineers, right, we just want to get the thing working, and knowledge graphs allow us to do both, and we can leverage a lot of the smart things that the ontologists and taxonomists have to say about the world and about how we should organize information. But if we want to link this thing to this thing for whatever reason, we can do it without worrying about breaking an entire system, right? And so they're really flexible data stores, and because they're analytics supported, we can build connections, we can break down connections, and be really agile with that because the analytic is really built into that process. So why would we build these things, right? What can we do with them? Well, you have search cards, which you just saw. We can retrieve facts about, people, places, organizations, information that people are most likely to want. And we can tailor this information by type, right? So if you search, you use your favorite search tool, whether it's Google or Bing or what have you, right? Use your search tool, you get a little knowledge card on the side. That card will change based on what you search for, right? So if you search for a person, you'll get one type of card. If you search for a place, you'll get another type of card. If you search for a movie, you'll get a third type of card, right? And sometimes it's even more granular than that. Sometimes even within people, you'll get different types of cards. So, actors might have different types of cards than soccer stars, who might have different types of cards than politicians, right? Countries might have different types of cards than cities. You might have a very tourism focused card for a city, whereas with a country, you might have like a, history, geopolitics focused card, right? Businesses, obviously, again, a big business, you're probably interested in stock prices and news, whereas a small business, you're probably interested in like, what are their hours? Are they open right now? Like, what's their phone number? Can I call them to see if they have this thing I want to buy? Whereas, if you Googled Microsoft and got the phone number for Microsoft, right? How helpful was that? You almost know you call in and nobody would pick it up. So you could tailor all that with knowledge graphs based on the linkages. Also heavily used in question answering, so generating answers to questions about the world, or your little slice of the world, that is. And knowledge graphs are heavily used in question answering because we can break the question that's being asked down into a statement, like in a query statement, for knowledge graphs, and knowledge graphs are really good at processing that information, because facts are stored for a lot of these question answering systems, they're stored in nice, neat triple stores, which maps very nicely to the question format, right? If I ask, is it going to rain today? We can map today to a period of time, and then rain to the weather, right? And so you're asking about the weather today, and then it'll look up, do a query for that, and that's how it's how Siri works. It's how Google's question answering works. It's how Amazon's question answering works for the Alexa device. They all use some form of knowledge graph behind the scenes to try to answer your questions. They also use a lot of kind of like hand jammed lookup statements, but that is neither here nor there. A lot of the dynamic question answering is knowledge graphs. Probably the most popular use of knowledge graphs is this recommendation use, and this is where I mean, recommendations are just a really popular use case broadly, and knowledge graphs are an effective means of addressing this use case because you can commingle heterogeneous data. So I can take, imagine I'm Netflix, I can take data about the way users are interacting with movies. I can take data about the movies themselves. So, this movie was of this genre and it contained this actor and this director. And then I can take information from the outside world about movies. Like, this is what Rolling Stone said about the movie. This is what Rotten Tomatoes says about the movie. This is what Roger Ebert says about the movie, right? And I can commingle all of that in one graph and use all of that information to make recommendations. And that's really powerful, because having all that data in one place means you can make use of it at the time of recommendation. So Netflix uses their what they call a content knowledge graph heavily in their recommendation engine, which is one of the most important parts from their perspective to their operation. Amazon and Walmart kind of similarly. Walmart's actually a really interesting case because they try very hard to come up with concepts around their products. So like they have concepts of substitutions. So, if you buy this, you will either buy product A or product B, but you would never buy both of them, right? Example of this might be like a washing machine, right? Like if you buy a washing machine, you're not going to buy another washing machine the next day, right? You're either going to buy this washing machine or that washing machine. You only need one. I would imagine. It depends how dirty you are, I suppose. The other products don't fall into that category. Like, you buy a t-shirt. Well, just because you buy one t-shirt doesn't mean you can't buy the other t-shirt, right? You can buy more than one t-shirt. And so they come up with these concepts around their products, and they try to link these things together using their knowledge graph and drawing those connections like explicitly in their knowledge graph. So they might have a connection, right? So this this thing you're buying is this color and it's this type of product, and it goes with all of these products, and it's commonly bought with this, right? And you link all these things together through the graph, and so you can actually hop around the graph and build likely carts with random walk methods and random processes, and very, very powerful. And a lot of that analytics that's done on top of that graph, a lot of that's done in Python. Very data science heavy activity. And then last but certainly least interesting is compliance. And this is a very popular use of knowledge graphs at big banks. I would imagine that increasingly companies will turn to knowledge graphs to try to comply with GDPR. But basically what you're doing is you're laying out the compliance restrictions either in the graph or in an analytic, and then you're tracking all your business activity through that graph, and comparing the two. This has been really powerful to detect financial fraud. All the big banks use it, use knowledge graphs towards this end. The FBI uses knowledge graphs to this end. And increasingly it's spreading into other areas of compliance as well. Anywhere where you have a sophisticated compliance regime that you need to comply with, knowledge graphs can be powerful to do that because of that commingling, and because you can modify your structure, and you can hop around. So, one of the things with knowledge graphs is everybody kind of thinks they're just graph databases, right? Which they can be graph databases, but they certainly don't have to be. The biggest knowledge graphs are developed as triple stores, so they're just kind of listings of facts. So in these subject, verb, object triples, where you have a subject, a verb, an object. So the subject might be, Python, and then the verb might be is, and then the object would be programming language, right? And so Python is a subset of the big category of programming languages, and that might be a fact in our triple store. And our database would just be, tens of thousands, millions of these, right? That's a pattern that Google uses. Facebook actually implements their knowledge graph as a vast network of SQL databases. So, to say that the knowledge graph is a specific data store is pretty misleading. You can have a knowledge graph built on relational databases, and really what that points to is the premise of, or I guess the punchline for you all, which is that a lot of the knowledge graph work is done in Python code, because a lot of it's analytics, a lot of it's data munging, data cleaning, data processing, natural language processing, machine learning of different stripes to process data and move data kind of up the data hierarchy, right? So over on the right here, this is the data hierarchy from classical information theory, where basically you have data, you have information, you have knowledge, you have wisdom. And our goal with knowledge graphs is really to use analytics to bring that data up to the knowledge tier, so that we can grab it at that tier and then work right at the wisdom tier, right? So if you have, if you have your standard business, right, a lot of the work that people are doing is taking data and moving it into that information tier. traditional software development has been trying to take data and move it into that information tier so that people can work at that knowledge tier. And with knowledge graphs, what we're trying to do is we're trying to take the data even up one level higher and say, okay, most of the work you're doing right now is at this knowledge tier. Let's try to automate the process of getting this data from the information tier to the knowledge tier. And then so you can work at the wisdom tier. This is the vision, the hope with knowledge graphs. I think the classical definitions of each of these, I'm a little fuzzy on it, so don't quote me, but the data tier is just kind of like facts. The information tier is facts stored in a usable, retrievable way. The knowledge tier is facts facts in context, I believe. And so this one is, so knowledge is, it's sunny today or was sunny today, right? Or it's raining outside, right? This might be information, but then knowledge would be knowing that, okay, it's sunny, so that means it's not raining, right? It's sunny, so that means I don't know, it might be a good day to play soccer, right? That would be something that's happening at the knowledge tier. And though the wisdom tier is where you want to be working, which is where you're thinking critically, analytically, creating new knowledge maybe, right? Applying it to other concepts, right? So if it's sunny here and it's a good day to play soccer, then it might be sunny tomorrow, or then something else, right? Let's see. Anything else I wanted to hit on this slide? Knowledge graphs feed with machine learning processes such as Python. So a lot, the punchline takeaway for this slide really is when we think about knowledge graphs, it's really common to think about them as data stores. The data store is a piece of the puzzle, but it's certainly not the most important piece of the puzzle. The most important piece of the puzzle is all the analytics that go around the data store and curate and cultivate the data that's there to make those connections so that we can draw data out at the knowledge level, right? And we can do that regardless of the underlying database. Some databases make it a lot easier. Triple stores, knowledge, or graph databases make it a lot easier to stand up a knowledge graph than, say, a network of SQL databases. But if you have a network of SQL databases, you can certainly make a knowledge graph out of your relational databases. And then, when it comes to the analytics and this analytics step, which, for my money is really the most important piece of the knowledge graph process, there are kind of 4 steps that I like to think about. The ingest step is where we're bringing data into the knowledge graph. And so here you would probably have Python code that does web scraping or a lot of database connections and requests. And maybe you're doing hashing and comparing data to other pieces of data to say, hey, is this ready to go into the database? Do we already have this in the database, right? We found this thing on the internet. Is it the same as something else we found? We found this thing in a database or on somebody's files, on somebody's, shared drive, right? Is it the same as what we have? Do we need to update it, right? That's a lot of analytics written in Python to crawl and gather for data. Then you've got this prepare phase. This prepare phase is when you're trying to construct these simple facts that are going to make up the foundation of your graph. And so you're trying to match entities. So, if we find the word Python, we're going to try to figure out, okay, are they talking about the programming language or are they talking about a snake? Are they talking about Monty Python, right? Which of the 3? What are we doing here? And then once we make that entity match, then we're going to propose potential new relationships, right? So if we find something to do with the Python programming language, that's new, we'll propose a new relationship between Python and whatever the entity is, right? So maybe we find something that says, PyBerlin is a Python related meetup group, right? We can draw that connection, and if we find that fact, we can propose that connection kind of in this phase. Then we go to the predict phase. This is after the prepare phase. We'll clean and we'll put stuff in the database. Typically, the predict phase, we go back into the database, and then we predict new linkages, right? So if we just found a bunch of new data, we're going to try to make the connections between that data denser based on our knowledge of other connection types. There are certain connections that can never go together, right? And so we might have rules that are either machine learning rules that the system has learned, or they're human curated rules, human design rules, algorithms where we go in the system and we say, hey, if you find this, also add this negative link between this and these things, right? Or if you find a connection here, also add connections here and here, right? So you can imagine, we find a link that says, company X owns company Y. And then company Y owns company Z, right? Well, then we know company X owns company Z. And so we might draw that link as well. A lot of that is going to be custom depending on your retrieval patterns. So depending on the types of queries that you're going to use to get the data back out of the database, you're going to do that more or less aggressively. The graph databases are going to make that predict step. They're going to loosen that up for you because you can do some deeper traversals and you can, do more hops along your graph. If you're not using a graph database, you're going to want to be really aggressive there, drawing those facts out. Because it is harder to jump from kind of fact to fact and make those logical leaps outside of a graph database. And then again, that's all Python, graph machine learning, basically. A lot of neural network code there, a lot of CNNs and LSTMs there. And then the last step, of course, is the power step, where you're powering some other application. So whether it's a search application or a recommendation system or a question and answering system, right? You're using the knowledge graph to power that system, and we're again, maybe Python if you want, right? You can do the queries in Python connector, and then serve it up through a Python-based web framework, right? All the way up to a front end, which maybe you serve in Python. Over here on the right, you can see a little architecture diagram of a knowledge graph from Neo4j. They're a graph database company. They make a open source graph database. It's got a decent community edition. And you can see here everything, all these little yellow, what are they? I don't know my shapes well enough. All those little yellow shapes, hexagons, I think. All those little yellow hexagons can be Python scripts, right? Or lots and lots of Python scripts. When you've got this NLP service over here, a lot of that's going to be written in Python. When you've got this machine learning service over in that Spark bucket, those are great places to have Python. PySpark probably. These little hexagons up top to bring the data in, that's in that ingest and prepare phase. Those are going to be different Python scripts to process different data. And then all this writing over here on the right hand side, that's going to be your powering phase, or you're bringing data up to the application with Python. And you'll notice here that there's kind of a loop. So we're always going to be going back into our graph as we're updating our graph. So we're bringing new information in, and we're using information that we have to augment the information we're bringing in as we bring it in, and then it's going to go around and around and around. So it's a really weird process, but it makes, if you think about it, we're using our knowledge of the world to improve how we're understanding new knowledge of the world, about the world. Or again, for a lot of business contexts, right? It's not the world, it's our tiny little slice of the world. So it might just be our customers, or what we know about our market, or what have you, right? So yeah, and I think that's my talk. So yeah, I'll end it there. I'll do a little recap. So what all did we cover today? So we covered kind of what knowledge graphs are, right? Knowledge graphs are these data management systems, right? They've got a database, typically a graph database, increasingly a graph database, but more importantly, it's a bunch of analytic scripts, systems, processes that augment that data. And make it usable as things, not strings, right? That's what Google calls it. Where Python can plug in is in all those places that augment the data. Python, as I'm sure everybody on this meeting knows, is an awesome language for data munging. Very, very high level, very clean, easy to read, fun to write. Right, makes working with data pretty fun, pretty easy. So it's super well suited for all those data cleaning tasks, and it's used in a lot of these machine learning and NLP scripts that augment knowledge graphs. Again, we're a little early on knowledge graphs, right? I think 2019 was the year of the knowledge graph, because I know a lot of these companies started to get into the knowledge graph space. I think really we're starting to see the momentum around graph databases pick up maybe last year, heading into this year. And I think you'll see knowledge graphs kind of trickle down to smaller and smaller and smaller organizations as more and more people start building them and standing them up, and the processes around them become accessible. Right now, they're not super accessible because you have to hire a legion of Python developers to manage them. But it's getting easier, and a lot of the stuff is getting more standardized. So I will leave it there. I'll end with a pitch for my first book, Mastering Large Data Sets with Python. So that will, that's a great text for how to design any of those data management scripts. Anything that's needs to deal with big data, parallelized, and process it to do something fun with it. And then knowledge graphs and deep learning is all about about how we use deep learning, machine learning, AI to augment knowledge graphs and do cool stuff with it, like question answering and recommendation systems. So I'll close there and take questions.
Thank you for the insightful talk, John. If there's some questions, you can write them in the chat or also on Twitch. I will relay them. Also, we have one question in the chat. Thanks for the super interesting talk. Would you say there is a revival of the semantic web idea coming around the corner?
Yeah, I think so. I mean, the semantic web idea, for those who don't know, is the idea that we would take the linking and tagging capabilities of the World Wide Web and take that to its natural extension, which was everything should become wikiized, right? Where, I can click on this and it'll take me to, something on your blog, and it'll take me to the relevant piece of information. As we saw the web kind of fracture, and maybe not fracture, but democratize with Web 2.0, it just got too complex, right? People, if you were just authoring a blog, it wasn't reasonable to ask you to also tag all of your content, right? You could barely figure out how to make the post and put the image in and respond to the comments. I think the technology supporting semantic web things has gotten a lot easier and a lot better. And as the research behind how to do graph computations more cheaply has gotten better, and graph databases help link a lot of this stuff together that are a lot easier. And there are organizations that are dedicated to trying to revive some of these concepts. I could definitely see some of the bigger entities try to lead the way. The question I would have is if we would be headed in the direction where you have a unified semantic web, or do you have fractured semantic webs, right? It's not entirely clear to me that Google and Microsoft and Facebook would all decide they want to be part of the same web. They might decide they want to share some semantic web pieces, but then hold other pieces separate, right? I think semantic web was fundamentally a open source concept, and maybe it'll be successful on the open source, but it's a lot of companies, right? They're naturally protective, and to the extent they want to promote the open source stuff, they promote it only when it's convenient for them. So the idea of linking the entire web together, may be useful, maybe not. If you're Google, do you want to, and you've got a huge advantage in understanding how the web links together, do you want to make that available to everyone and undercut yourselves in the market? The same with Microsoft or Facebook or Yahoo, right? Probably not. So I don't know if that's a good answer, but I think semantic web concepts are being used heavily in enterprises right now, and whether or not they'll catch on and be sticky on an internet scale, I think is TBD, but they're definitely making a little comeback.
We have another question. Is Python also used for graph theoretical analysis in these contexts you described? If so, what's currently the state of the Python tooling libraries in this domain?
Yeah, so Python doesn't tend to be the language of choice for theoretical graph analysis. A lot of that heavy theoretical analysis is either just mathematical, or it's written kind of lower level with like a C++. Haskell is pretty common in theoretical math and theoretical computer science fields, because it's functional and very mathy. Python is the language of the practitioner. So a lot of what happens is the approaches graduate from theory to practice, and somebody will translate a math paper into a Python implementation, or they'll take a C++ implementation and wrap that with Python. And those tend to be the two approaches that we see, and how we see Python interact with a lot of the graph theoretical stuff.
Great. Thank you for the cool talk.
Fantastic.
Yes. So if there are no more questions, we'll move to the next talk.
Thanks so much for having me, guys.
Thank you, John. So the next talk is A Slice of Python by Naomi Sidder. Naomi, feel free to start with your presentation.
Okay, fine. Well, just give me a second here while I get this ready to share. Okay. Let's do that. There we go. I hope that you can actually see my screen at this point. Let's see here. I'm still trying to get one thing to work, and it does not seem to want to show my speaker notes. That's a little bit of a disappointment here because I've got some live coding to do. Let me unshare and come right back. I think that will maybe be the best thing that I can do. So apologies for that, but I think I need to do that. So let's see here. I'm not actually. There we go. All right. This time for sure. There we go. Now I have my notes. I'm sorry about that, but when you get to a certain age, you need your little memory aids. So you should be seeing my initial slide. So again, I'm Naomi Sidder. Delighted to be with you. I wish I could be with you in person. I think it's been a couple of years since I've been to Berlin, but who knows? Maybe one of these days, again, that will be possible. Contact information, you can find me on Twitter. NaomiCedar.tech is where I have a few things on the web, not much. And this talk is a Jupyter notebook that you can find at this particular address on GitHub in Sidder/talks. I'll show that address to you again at the end. Or if somebody wants to be helpful and type that into the chat, that would be cool. So I'm going to talk about something that's kind of basic, but it's also got some interesting things about it that I think most people don't know. And that is, I want to talk about slices. And you know, if you've done much with Python, you've done some things with slices probably. And let's just kind of quickly review some slice stuff. So if we have a list like this, we can do something like, say, we can go up to, but not include index 3 and get a slice like that, you know, or we can do the opposite and we can go from index 3 and get everything that's there. And of course, if we don't give any indices at all, just the 2 points, we get the entire list. It's a copy of the list. Be careful, it's not a copy of the contents of the list, but it's a copy of the list. We can even do fancier things like, say we're going to take every other item. We can set the step value to 2, and that'll give us every other item. We can even, just in case you've forgotten, we can even start at the end and go backwards. So we can reverse things, doing things like that. So that's all, you know, pretty basic slicing stuff. And of course, there are cooler things you can do with slices. So, you know, you can change a slice by just setting that slice equal to a new list. If you want to add items, you can set a slice to a larger list. You can even set an empty slice to a larger list, which we'll insert. You want to remove items, you can go in the opposite direction. You can set a slice equal to a smaller list or even an empty list, which will delete everything in that slice. And in fact, the items in the slice don't even need to be contiguous. So let's have a look at some of this stuff here. So again, as I say, we can do things like we can change a slice. So I can do things like a list. We were going to go 0 to 3. I can set that equal to a new list 10. Let's do 20, 30. Okay, and then let's see what that will get us. Oops. So I can do that, and notice that for the first 3 items, up to but not including index 3, I've replaced that with 10, 20, 30. Okay, that's cool. I could even do something like I could insert in front of slot 3. Oh, let's use some different numbers here. So this is the empty slice that is right here, right before index number 3, right? And with slice notation, we go up to but not including. So this means there's nothing here, but we're going to put something there. So we can do that. And sure enough, we've inserted those 2. And we can of course do exactly the opposite, and we can set a slice equal to nothing. So we can do that. And here we've taken index 3 and 4 out by setting it equal to an empty list. So that's all. It's slice notation. It's a little bit more advanced, but it's still not that surprising. Now, the last thing I said, you remember, was that we can actually do things when they're not contiguous elements. So here's what I want to show you that's a little bit interesting. Let's do the odd indices. So we do that just so you see what we're talking about. We're starting with 1, and we are going 1, 3, 5. We're starting at 1 and taking every other item. Okay, let's set that slice equal to 10, 30, 50, for example. Now, here's the question, and I wish, this is where I really wish we were alive together, because we could get more entertaining answers. But what do you think's going to happen here? Is this going to be an error? Or is this actually going to work? And if it works, what do you expect it to do? Okay. Again, if I were in person, I would be looking significantly around the room. Let's see what it does. Oh, well, I need to actually show it to you, don't I? All right, there we go. And in fact, we managed to replace 1, 3, and 5 here, those indices. And this will work. It's surprising. I think a lot of people don't know. This will work as long as the slice we're using is exactly the same length, has exactly the same number of elements as the slice we're replacing. If it doesn't, then you can't do this, where you're actually just kind of replacing things that aren't a contiguous chunk. But it works. So slices are cool. But this is what I really want to do with you today, is I want to experiment a little bit and look at the question of, what is a slice? How does it do that? And to do this, I want to take kind of an experimentation approach. And I think this is kind of my second sort of sneaky message today. I want to show you a little bit about how you can think about experimenting and poking at and finding out how pieces of Python work. I'm a big believer in this, because when you do that, you end up getting kind of a fundamental understanding of how these pieces work that leads to you reasoning and thinking about them more reliably, which means you end up having to fight fewer bugs, which is always a good thing. In fact, I mean, since we're kind of on a Manning day with two Manning Publications authors. I'm working for Manning Publications on a live project, sort of a combination of text and video to do that. So you can look around by sometime during the summer. There will be Exploring Python Fundamentals live project that takes this approach. But in any case, let me show you what I mean by this as we take apart how slices work. So we know that slices use square brackets, okay? That means that they call the dunderGetItem method of the object that they're stuck onto. Okay, you saw that when I was working with A-list. A-list square brackets means I'm actually calling A-list dunderGetItem method. So what I want to do with the remainder of our time here this evening is actually make an object and make its dunderGetItem not only do things that a dunderGetItem method should do, but also have a little bit of instrumentation. I want it to show us what it's doing a little bit more. Okay, so to do that, I'm going to create this class that I call reflector. And I call it reflector because if you give it something in square brackets as an index, whatever that might be, it's going to try to reflect it back to us. Okay, so how are we going to do that? Well, we're going to define a getItem method. Need self. We also need the parameter to indicate what we're getting. I'm going to call this index. Could call it anything. And the first thing I'm going to do is I'm going to add my instrumentation. So I want to know what type and what value index is every time I call dunderGetItem. Oops. Let me fix dunderGetItem so it really is dunderGetItem. Okay. So what I'm going to do, index, I'm going to use the type function. So that should give me the type of index. Actually, let me make it clear. There, that'll be better. And then I want the value of index itself. So with the magic of F strings, that's all pretty easy. So that's my instrumentation. Now, I'm going to make my reflector basically follow very simple sequence semantics. That is, you can start with an index of 0 and we'll go up to some point where we actually want to stop it. And you see here, I've got a limit attribute that will tell me when to stop. So we can say that if our index is 0 or greater, and it's less than self.limit, all we can do is return the index. This is the reflector part I mentioned. And we can make it do other things too, but this is just a very simple case here. Okay, if it's not between 0 and our limit, if it's not in that range, Python would expect something with sequence semantics to return an index error. So that it, not to return, excuse me, to raise an index error. Okay, so this will look to Python kind of like a sequence object. Actually, it'll look very much like a sequence object. Let's see if I made any syntax errors. No, that works. Okay, so here I've made a reflector and I've set my limit at 5. So basically we have a 5-slot reflector here. Now, if I try to get the first index, it says index is 0, and it tells me that my type is an int, and it is, and that it is 0, and it is. And, you know, I could do the same thing with 1, and it would, well, I need to put the 1 in there, and it would do the same thing. And if I were to do something like 6, which is clearly beyond our limit of 5, it's going to give me an index error, which is, after all, exactly what I told it to do in that circumstance. Same thing if I do a -1 because I haven't implemented negative indexing. Same thing, I get an index error. Okay, it's a very simple thing, but it lets me see how this thing works. Okay, now here's my first challenge for this, just so that you understand how simple sometimes these things are in Python. If I do this, again, I wish I were there in person to look at you significantly. Is this going to work in a for loop? Is my reflector actually going to be an iterable? That's my question. Okay. And I'm just pretending that I'm getting a mixture of yes and no answers, because that's what usually happens when I do this in person. So let's see what happens. And you see, it works fine, in fact, in a for loop. And I get 0, 1, 2, 3, 4, which is exactly what you'd expect. And you can see we call get in item, excuse me, with 0, 1, 2, 3, 4. And then we called it with 5, which would throw the index error. And that's what the iterator that is managing the for loop sees as a signal to stop the loop. So even though that was thrown behind the scenes, we don't see it here. This is a normal loop terminating normally. Okay, well, that's cool. So that's good for indexes that are integers, but what if our index, what if we're actually using a slice? Okay, now again, I just want to do a quick refresher here. If we're doing a slice with a list, we can do something like this again, and we can do 3, and we get the first 3, so that's fine. And if we try this with our reflector, so we try this with our reflector. Here again, I want to pause for just a second. What do you expect is going to happen? Okay, I know you're all thinking about this at home. What's going to happen is we get an error. Basically, we get an error saying that you can't compare. Let me scroll down just a hair. That you can't compare an int and a slice. But wait, slice? We back up and we can see from our instrumentation that what we have passed in to get item is a slice object. And in fact, here it is. It's a slice object with 0, 3, and none as its parameters. So this is interesting. This is a thing. So we're not passing in 0:3 when we use this. We're passing in a slice object. So what this means, what this tells me is that when we use the colon between square brackets, behind the scenes, Python is creating a slice object and using that. So that means we need to understand a little bit more about a slice object, right? I mean, again, if I were in person, I would do a quick survey. How many of you knew that there was a slice object, and how many of you knew it was always created when you used the 2 colon, or the 2 points, the colon, between square brackets? Okay, so let's look a little bit at a slice. So it turns out there is a slice function that will create slices for you. It's a built-in function. And as we saw, it gets parameters. So we can do things like 1, 3, and we can create a slice. And notice, since we didn't give it a third parameter, which we would if we were doing a step, third parameter here is stored as none, but we have a slice object on our hands now. And if I take a list, which understands slices, I can use my slice object the same way I would use slice notation. So I can do that. And I get from 1 to 3. I get 1, 2, stopping before 3. So in other words, I can actually make my slices into variables if I want to. And it's interesting, you might even want to. For example, suppose I were to decide I wanted a slice that would always get me the even numbered indices of a list, every other one starting from the second one. I could, of course, always use : 2 in square brackets, but I could also just make that store that as a variable. So I could do things like, if I've got a list here again, I can do a list evens, and it will work. And in fact, that will work with any size list. So I have a generic get every other item slice here. Interesting. Oops, don't want to do that. Okay, so this is interesting. The next thing I try to do when I'm poking around looking at how something in Python works is I like to look at its dunder-dict property. Now, not everything has a dunder-dict property, but if you do, you can see the things that belong to that particular object. They aren't inherited. They're the things that are actually there in the object. That's why I use dunder-dict rather than the dir function. So if I do that, you can see we got a repr. Okay, have a hash, except it's not hashable, so that's none. It's got get attributes, it's got less than or equal to, the various comparison things. It's got a new, it's got a method indices. That's interesting. We might want to talk about that. It's got a method dunder reduce, which we're not going to talk about. It's mainly used for pickling. I don't want to talk about pickling. Notice we got a start, stop, and step, which are the ones that we've been seeing. You know, those are the pieces of a slice that we're used to thinking about. And we've got, of course, our doc string saying that a slice you can create by using slice, start, stop, step, and that'll create a slice, which is what we just did. So, okay, that's not bad. So yeah, we've got these things here. We've got start, stop, and step. Those are all pretty common slicey things. And I mentioned that we have this indices method. And that is not quite as obvious, but that's worth having a look at what that is. So, of course, the other thing that you can do when you're looking at something in Python you don't know about at a prompt is you can use the help function. So let's do that. And it's telling us the stuff about slice that we sort of already know, but let's go down here. And here we have indices. So indices takes a length, and what it does is it will figure out, given the slice that you're working on and the length you give it, and the length of a sequence that you give it, it will figure out where, if you had a sequence, a list, or whatever it might be that long, where it would start, where it would stop, and what its stride length would be. So it'll figure stop, start, and step out for you, given a particular length that it's supposed to go with that slice. And this is handy because if you have out of bounds things, like, you know, in Python, it's legal for us to have a list with 5 elements, and we can say, we want the slice that's from 0 to 66. And that doesn't throw an error. It just goes to wherever the list would normally end and stops. So it will figure that out for us if we use the indices method here. So that is helpful. Okay, so that's pretty cool. And in fact, if I've got, you know, I did our a slice remember here, if I call indices on it, and I can use, well, the current size of our reflector is 5, so let's use that. So if I start with this slice and I say, okay, given that we've got 5 items, what are my start, stop, and end? It'll tell me you're going to start at 1, you're going to end before 3, and your step is 1. So it's figured that out. If I change this to be something else, it's going to give me maybe a different answer depending. In this case, it won't. If I give it 30, say, it's still going to be the same because we gave it an endpoint. But if there was something without an endpoint, it would figure that out properly. So yeah, that's one thing about slices, but we're still not quite to where I want to be. And that is, I want to now make my reflector object handle slices. And this is not as hard as you might think. So the first thing I'm going to do here right after my instrumentation is I'm going to check to see if I've got a slice. Okay, if I've got a slice, I'm going to use step equal index. I'm going to use this indices method to tell me where my slice starts, stops, and what its step is so that I can extract that and pass it back. Okay, and my length is going to be self.limit again here. Okay, now the way I'm going to make my slices work, remember, I'm just passing back the index. Like if you say slice 0, I just give you back a 0. In this case, I'm going to give you back a list of all of the indices that would be there. Okay, so for that, I'm going to need to have an empty list to put my results in. Okay, and then I'm going to go through things. I'm using a while loop here just to keep things simple. It's not necessarily that I would always recommend using a while loop. This is just making things very simple here. So, oops, I'm going to set my x equal to start. And then I'm going to say while x is less than stop, just following our slicing thing, I'm going to add the current index to my list of results that I'm going to return. And then I'm going to add my step value to x. And if I get through all of that, I'm going to return results. Okay. And that will, if I've got a slice then, oops, I think I went too far there. That would have been a syntax error. If I've got a slice, it will generate all of the indices that it would return. If I don't have a slice, it's then going to do the thing assuming that it's an integer. And if it's legal, return that. Otherwise, it's going to return that here. And I've got basically, there we go. So that's all we need to do, theoretically. I mean, let's see if I've got a syntax error or something here. No, apparently I'm fine. So I made another reflector of size 5. And if I just do this, it's going to say, yes, it's a reflector object. Okay. And if I do 1, it's going to return 1. Okay, fine. If I retry, say, 3, okay, this should give me 0, 1, 2 back. Let's see if it actually does that. 0, 1, 2. So it does that. And again, index is a slice. This is my slice starting at none, 3, none. Okay, well, so this is pretty cool. And in fact, I can use, let's see here, I can even use something like my evens slice here. Let's see if that works. 0, 2, 4. Hey, I'd say we're pretty cool. So in fact, that's all we need to do. That's what a slice does then, is keeps track of start, stop, and step. And it uses the indices method to help it do that, or to help other things use that. So that's cool. There's one last thing I want to bring up, and that is multiple slices, extended slicing syntax. So if you try to do 2 different slices in square brackets with a list in Python, with most of the Python built-in types, it's going to return syntax error immediately. It's not going to try to do anything with it. But if you're in something like NumPy or Pandas, you actually can give it more than one slice in the square brackets. There are various funky things you can do. So I thought it'd be good to finish up with having a quick look at what happens there. So I'm not going to bother to load NumPy or anything like that. But what I'm going to do is I'm going to make a bigger reflector. I'm going to call it a big reflector. And I'm going to make this have 100 slots. And then I want to do something like this, excuse me, like this. I want to get 10 to 20. And I also want, let's say, 30 to 40. Now, all I want to do is I just want it to string those all together. Now, if you're using something like NumPy or Pandas or whatever, you might actually be getting a sort of a 2-dimensional slice out of a grid or something like that. They're doing much fancier things. I want to keep this simple so that I can see what works, and I don't care about the problem I'm solving so much. So I'm going to do this, and here, again, let me make one of these ominous pauses and ask, what do you think is going to happen? Are we going to get a syntax error? Are we going to get some other kind of error? Is it miraculously going to work? Nah. Let's see. Let's see what happens. Okay. Oh, sorry. I screwed that up. This is the other good thing about being in person, by the way. One of you would have yelled out to me that I was doing that and saved me having to go through that extra step. But it works now. So you can now see that we got an error, and we're back to getting the error we got when we didn't have slices implemented. And that is, this comparison here doesn't work because you can't directly compare int and tuple, which means, of course, that what we got passed in when we did this was a tuple. And in fact, it was a tuple of slice objects. Now, that's not too surprising, really, because in general, if you've got some stuff in Python separated by commas, whether it has parentheses around it or not, it's really going to be behind the scenes be a tuple. So we've now got a tuple of slices. Okay, let's, just for the sake of argument, let's go ahead and change our implementation of our reflector so that we can see that. Okay. So we're going to do a couple of things here. First of all, and this is to make the code a little bit simpler, if we have a slice index, what I want to do is I'm going to say it now becomes a one element tuple containing index. So all I'm going to deal with, I think, is I just want to deal with tuples of slices, so that lets me do that. Okay, so then we say, okay, if is instance, if our index now is an instance of tuple, and if we use a slice, it will get turned into a tuple. If we're going to use multiple slices, that will be turned into a tuple. So that will let us do that. Then what we're going to do is we'll kind of reuse this code, but with a few changes here. So first of all, we have now index is a tuple, so we need to iterate over that tuple. So that will get this the ability to iterate over things like that. So that's fine. We still want to have our results. So let me go back up and add that, because we're still going to need to have a list of all of the results to return. So that's an empty list. Okay. Now I'm going to do the same thing I did before, which is I'm going to say, actually, let me just pop it up here. I'm going to say that start, step, etc. is the same thing, and I'm going to use the indices method, but I'm going to use it for each individual slice as I iterate through, not the overall tuple of slices or anything like that. So we'll do that. We still want to do that. We actually now need to have a separate set of results for each index we go through. So I'm going to do this. I'm going to make an I results here. Okay. So now we're set up. Okay, I still, for each index, want to do my while loop like that. And I want to do that. Of course, I want to append that to this here. So that's fine. And I want to do that. So I want to do my stepping through. So this code is pretty much the same as what we used for one index. And now we just have it inside our loop as we iterate over all of the indices. So that's fine. What I want to do, though, is I want to extend that list of results here with I results every time I get through it. Okay. And then when I'm all the way done going through all of the indices, I'll just return my results. And of course, if it's not that, if it's an illegal index, I want to do this. I also want, where are you here? I also want to do my, if it's anything else at all, I want to raise my index error. So let's keep that legal. All right, and now let's see if I manage to make that work without a syntax error. Apparently. Okay, so now let's go ahead and let's try this again. So I'm going to make another big reflector. And I'm going to have to redeclare this because I now have a new reflector class. Okay, so that worked. And now let me go ahead and see what happens if we ask big reflector for 10 to 20 and 30 to 40. Okay, here again, another significant pause. Do you think this is actually going to work? It actually worked. Look at that. So we got two slices, 10 to 20, 30 to 40. We got 10 stopping just before 20, 30 stopping just before 40. So that's all that it took to implement this. And that's part of my message here, which is, you know, kind of wrapping things up. Slices are, again, just so Python. And by that, I mean, they're really kind of simple objects and you can take them apart and see how they work, but they have almost endless possibilities. And as I was saying, the other thing that I wanted to get across here is that the fun of Python for me, certainly, and I hope for you, is sometimes in the exploration. And I hope you get an idea here of how you can create your own experiments, although maybe you'll spell experiments better than I did, and test your assumptions by making your own simple objects and then kind of putting them through their paces and just sort of exploring how the language works. So that really is what I have for you. Again, you can find a version of this notebook on GitHub, and I thank you very much, and I would be happy to entertain any questions.
Thank you, Naomi, for the insightful talk.
My
if there
pleasure.
are any questions, just post in the chat. I have a question, actually. So you're involved with the Python Software Foundation. What is your view? Are there going to be any changes in this area of Python around slices, or probably not?
No, I think I didn't go back and do the research on this. The slicing notation has been around for a very long time. If in fact there were some other need for some sort of extended syntax, then maybe that would be added. But I can also tell you that as I observe the discussions, I think that it would be a very tough thing to talk people into. But if several different, say, data processing, machine learning, whatever systems decided they needed yet something else in here, then there might be some change in that. There was actually some discussion about, what was it? It was something about more related to dictionaries, about allowing named indices in there, sort of like we have named parameters to a function, doing something similar with indices. That came up on Python Ideas, and last I saw, I don't think it was going anywhere. It was interesting, but going to introduce a lot of complexity, I believe.
I see, thanks.
Okay.
So if there are no other questions, we can move to the closing part.
Yeah, as usual, thanks so much to all of you, our attendees, for joining today's PyBerlin. Thanks also to today's speakers, Ivan, John, and Naomi, for sharing their knowledge with us today, and to our sponsor, ScoutBee, for providing us with a premium Zoom account. And of course, thanks to our other sponsor, Manning, for making this month's PyBerlin possible. Our next meetup is scheduled to take place on June 21st, on a Monday. Everyone is very welcome to contribute to PyBerlin, and we can always use some extra help. So please reach out to us if you're interested in helping out. We're also looking for people willing to speak at PyBerlin. So if you have an idea, you can submit it by using the form linked on the slide. Don't forget to spread the word about PyBerlin, and enjoy the rest of your week. Take care and see you next time.